July 18th, 1944. Hamarøy Municipality, northern Norway. Lieutenant Mattholie of the Royal Navy's 1841 Naval Air Squadron pushed the Chance Vought F4U-1A Corsair through deteriorating weather conditions as anti-submarine patrol duties stretched toward their conclusion. HMS Formidable steamed south towards Scapa Flow following Operation Mascot, the latest attempt to cripple the German battleship Tirpitz. Technical problems developed rapidly. Engine instruments showed troubling readings that demanded immediate attention. The Pratt and Whitney R2800 double Wasp radial engine, normally smooth and reliable, began displaying symptoms that left Mattholie no choice but to seek emergency landing options. Below stretched Norwegian territory still firmly under German occupation. The lieutenant scanned the rugged landscape for suitable landing sites, knowing that every moment brought him closer to forced abandonment of his aircraft or worse. He spotted a field near Bodø that appeared adequate for emergency landing procedures, despite less than ideal conditions. The distinctive inverted gull wings of the Corsair, serial number JT404, descended through the thin overcast. Mattholie executed a controlled crash landing that demonstrated his skill as a naval aviator. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The F4U touched down hard in the Norwegian field, but remained largely intact. Mattholie climbed from the cockpit, assessed his situation quickly, and recognized the inevitable truth. German forces controlled this territory completely. Within hours, Wehrmacht personnel arrived at the crash site to secure both pilot and aircraft. Lieutenant Mattholie's war as a combat pilot ended abruptly. He would spend the remainder of the conflict as a prisoner of war at Stalag Luft 1. But the Corsair, designated JT404, was about to embark on a second, operational life that would provide German engineers with an education about American industrial philosophy, engine technology, and design priorities that fundamentally contradicted assumptions carefully cultivated by Luftwaffe propaganda. The Germans had captured what many American pilots and Japanese opponents considered the most formidable fighter aircraft in the Pacific theater. Over the following months, as Luftwaffe engineers systematically examined, repaired, and eventually flew this captured Corsair, they would confront uncomfortable realities about the technological gap between American and German aviation engineering. The F4U Corsair represented American willingness to pursue unconventional solutions when conventional approaches proved inadequate. German engineers would discover an aircraft powered by an engine that produced substantially more power than Germany's finest radial engine, while demonstrating reliability, manufacturing quality, and material abundance that German industry could no longer match. The inverted gull wing configuration that gave the Corsair its unmistakable profile would reveal sophisticated engineering that solved multiple design problems simultaneously, while accepting weight and complexity penalties that resource-constrained German designers could never consider. The capture of JT404 was not the first time Luftwaffe pilots had encountered Corsairs in combat, though such encounters remained relatively rare in the European theatre. The Royal Navy's Fleet Air Arm had deployed Corsairs to operations in northern waters, flying from carriers during strikes against German naval targets, including the Tirpitz. German pilots who had faced Corsairs reported an aircraft with exceptional speed, powerful armament, and remarkable structural strength that allowed it to absorb battle damage and continue functioning. Combat reports noted the distinctive sound produced by the massive three-bladed propeller cutting through air at high speeds, a characteristic whistle created by unique aerodynamic properties of the design. Japanese pilots facing Corsairs throughout the Pacific had developed deep respect bordering on fear for what they called various names but universally recognized as a dangerous opponent. American naval aviators flying Corsairs had achieved an 11-to-1 kill ratio against Japanese aircraft by mid-1944. The aircraft's reputation in the Pacific as a devastating fighter bomber had reached even German intelligence services, but direct examination of a complete, relatively undamaged example provided opportunities that fragmentary combat reports could never supply. German salvage teams recognized immediately the intelligence value of recovering JT-404 intact. Standard procedures developed through years of systematically recovering crashed Allied aircraft across occupied Europe swung into action efficiently. The Corsair received armed guards to prevent sabotage or unauthorized access. Specialists assessed the extent of damage and determined whether the aircraft could be repaired to flying condition. Initial examination revealed that despite the forced landing, the airframe remained structurally sound, with no catastrophic damage to major components. The engine showed no obvious signs of terminal failure. Control surfaces remained attached and functional. The landing gear, though stressed by the emergency landing, had not collapsed catastrophically. German technical officers concluded that with appropriate effort, replacement parts cannibalized from other wrecks if necessary, and skilled technicians, JT-404 could be restored to flying condition for evaluation purposes. The Luftwaffe interrogators who questioned Lieutenant Mattholie attempted to extract information about the aircraft's systems and operational procedures. Specifically, they pressed him repeatedly to explain the wing folding mechanism that allowed carrier-based Corsairs to reduce their wingspan for shipboard storage. The lieutenant, following his training and obligations under military law, refused to provide technical information that might assist the enemy. His silence on this particular point frustrated German engineers who understood that proper wing folding procedures were essential for transporting the aircraft by available means. Unable to obtain cooperation from the pilot, German personnel carefully examined the wing folding mechanism directly, attempting to deduce proper procedures through observation and experimentation. Eventually, they concluded that attempting to fold the wings without complete understanding of the system risked damaging the complex mechanism. Instead, they opted to transport the aircraft by boat, ferrying JT-404 along the Norwegian coast toward facilities where detailed technical evaluation could proceed under controlled conditions. The Corsair began a journey that would eventually bring it to Germany itself, destined for Erprobungsstelle Rechlin, the Luftwaffe's premier testing facility located approximately 100 kilometers northwest of Berlin in Mecklenburg. Rechlin served as the central German military aviation test facility, roughly equivalent to Britain's Royal Aircraft Establishment. Every new German aircraft design underwent evaluation at Rechlin before entering production. Captured Allied aircraft that could be restored to flying condition were systematically tested there to gather intelligence about enemy capabilities. By late 1944, Rechlin's captured aircraft evaluation program had become highly systematized. Specialized personnel had developed extensive experience repairing Allied aircraft despite lacking original technical manuals, factory specifications, or genuine spare parts manufactured to original tolerances. The facility maintained an inventory of components salvaged from multiple crashes, allowing technicians to cannibalize parts from several wrecks to create one flight-worthy aircraft. German records from 1944 list JT-404 at Rechlin under repair, indicating the facility had received the aircraft and begun restoration work. The repair process for Matholie's Corsair would require substantial effort and considerable improvisation. Technicians needed to assess every system thoroughly, determine which components required replacement, locate or fabricate necessary parts, and verify proper function before risking test flights. The Pratt & Whitney R28008 double Wasp engine demanded particular attention. This massive 18-cylinder radial engine represented American powerplant technology at its finest, and German engineers approached it with professional curiosity mixed with appropriate caution about working with unfamiliar systems. The context surrounding JT-404's capture and subsequent evaluation extends beyond the individual aircraft to encompass the broader strategic situation facing Germany by mid-1944. Allied air superiority over Western Europe had become overwhelming. The Normandy invasion on June 6 had succeeded despite Germany's best efforts to prevent it, in large part because Allied air forces controlled the skies above the beaches completely. German fighter forces, once dominant, now fought desperately on the defensive across multiple fronts, while suffering unsustainable losses in pilots and aircraft. The strategic bombing campaign against German industry was reaching its peak intensity. American heavy bombers, escorted by long-range fighters, struck targets deep inside Germany with increasing frequency and effectiveness. German production of aircraft, engines, and military equipment continued despite the bombing, but quality control deteriorated steadily as strategic materials became scarce and Allied attacks forced dispersal of manufacturing to smaller facilities scattered across the country. Skilled workers had been drafted into military service or killed in bombing raids, replaced increasingly by forced labor with minimal training. Into this deteriorating situation came the captured Corsair, offering German engineers an opportunity to examine directly an aircraft type that represented American naval aviation at its most capable. The F4U embodied design philosophies and engineering priorities that differed fundamentally from German approaches. Where German designers optimized for maximum performance within severe resource constraints, American designers appeared to optimize for mission effectiveness with minimal constraint on resources consumed. Where German engineers made careful calculations about acceptable risk versus weight savings, American engineers appeared to add strength and redundancy systematically. Most significantly, where German industry struggled to produce adequate quantities of even simplified designs using substitute materials and degraded quality control, American industry appeared to manufacture complex, sophisticated aircraft incorporating advanced technologies as standard equipment with no evident compromise in quality or materials. This contrast between American abundance and German scarcity would become painfully apparent as Rechlin engineers examined JT-404 in systematic detail, according to standard evaluation procedures. The F4U-1A that Lieutenant Mattholie had flown represented a mid-production variant incorporating refinements developed from combat experience in the Pacific Theater. The aircraft had evolved considerably from the original XF4U-1 prototype that test pilot Lyman Bullard first flew on May 29, 1940. That prototype had immediately demonstrated exceptional speed, exceeding 400 miles per hour in level flight, and becoming the first single-engine American fighter to break that significant threshold. The speed came from systematic optimization of the complete airframe around the most powerful engine available. In February 1938, the United States Navy Bureau of Aeronautics had requested proposals from American aircraft manufacturers for a new carrier-based fighter airplane with performance exceeding anything currently flying. During April, the Vought Aircraft Corporation responded with multiple designs. The proposal, powered by Pratt and Whitney's developmental R2800 engine, won the competition in June, and Vought began detailed design work immediately under Chief Engineer Rex Beisel's leadership. Beisel's team faced a fundamental design challenge that would define the Corsair's distinctive appearance. The Bureau of Aeronautics had selected the R2800 specifically because it represented the most powerful air-cooled engine available, producing 1,850 horsepower from 18 cylinders, arranged in 2 rows of 9 around a massive crankshaft. Extracting maximum performance from this powerful engine required a large propeller with sufficient diameter to convert horsepower into thrust efficiently. The engineering calculations indicated optimal propeller diameter of 13 feet 4 inches, far larger than any previous single-engine fighter. This enormous propeller created an immediate problem. Standard fighter configurations with straight wings extending directly from the fuselage could not provide adequate ground clearance for a propeller of such diameter without using landing gear struts so long they became structurally impractical and excessively heavy. Lengthening the landing gear enough to clear the propeller would raise the cockpit to heights that made carrier deck handling difficult and created dangerous instability during ground operations. The solution required innovation beyond conventional thinking. Engineer approaches to the propeller clearance problem progressed through multiple iterations before settling on what became the Corsair's signature feature. Beisel's team considered various options, including retracting the main landing gear rearward rather than inward toward the fuselage. But for the wing, chord they had selected, making landing gear struts long enough while maintaining adequate strength, proved extraordinarily difficult. The breakthrough came when someone proposed bending the wing itself, creating an inverted gull wing configuration that mounted to the fuselage at a downward angle before extending outward horizontally. This unconventional wing design solved multiple problems simultaneously through clever geometric optimization. The wing root, where it attached to the fuselage, could be positioned relatively high on the fuselage sides, maximizing internal fuselage volume while providing a strong attachment point for structural loads. From this high attachment point, the wing bent downward at a pronounced angle for approximately 3 feet, then transitioned smoothly to horizontal extension outward to the wingtips. The landing gear attached at the lowest point of this bend, at the crook, where the wing transitioned from angled to horizontal. This attachment point allowed the landing gear struts to be relatively short, while still providing adequate propeller clearance when extended for takeoff and landing. Shorter landing gear meant lighter weight, greater strength, and improved reliability compared to the extremely long struts that straight wings would have required. Additionally, the perpendicular angle where the bent wing section met, the landing gear attachment point, allowed the gear to retract straight upward into the wing with minimal internal volume required, maximizing fuel capacity within the wing structure. The inverted gull wing configuration also provided aerodynamic benefits beyond solving the landing gear problem. The junction where the wing met the fuselage occurred at nearly a right angle, minimizing interference drag that typically plagued wing fuselage junctions. The transition from angled to horizontal wing section occurred smoothly, with carefully fared contours that maintained good airflow across the entire wing surface. The final design represented sophisticated engineering that accepted substantial manufacturing complexity in exchange for solving multiple difficult problems through a single integrated solution. German engineers examining the captured Corsair would recognize the inverted gull wing as evidence of design philosophy that differed fundamentally from their own approaches. German designers facing similar problems would likely have pursued solutions that minimized manufacturing complexity, even if that meant accepting compromises in other areas. The bent wing required complex tooling, precise manufacturing, and careful quality control to maintain proper alignment and structural integrity. Each wing assembly represented significant manufacturing effort compared to simpler straight wing designs. But American industry appeared entirely willing to accept this manufacturing complexity. Vought had developed production processes that could manufacture the complex wing assemblies reliably at scale. Goodyear and Brewster, which received contracts to produce Corsairs under license as demand exceeded Vaught's manufacturing capacity, also implemented these complex manufacturing procedures successfully. The bent wing was simply how Corsairs were built, with no apparent consideration of simplifying the design to ease production even as manufacturing rates climbed to hundreds of aircraft monthly. The wing structure itself demonstrated American engineering priorities clearly. Primary load-carrying spars were forged from high-grade aluminum alloys that provided excellent strength-to-weight ratios. Secondary structure incorporated careful optimization to minimize weight while maintaining adequate safety margins. The wing skin, formed from aluminum sheet, attached to internal structure through thousands of rivets installed according to specifications that ensured proper load distribution and fatigue resistance. The entire assembly reflected manufacturing precision and quality control that maintained design intent throughout production. The wing accommodated 6 Browning M2 machine guns of 50 caliber, with 3 guns mounted in each outer wing panel. German engineers would discover during their examination that American designers had installed each weapon in an electrically heated gun bay to prevent freezing at high altitude where temperatures routinely dropped to -60 degrees Fahrenheit or lower. Heating elements drew electrical power from generators driven by the engine, representing additional system complexity that American designers included routinely to ensure weapon reliability under all operational conditions. Ammunition for the 6 guns was stored in boxes built into the wing structure, with each gun fed from its own dedicated ammunition supply. Total ammunition capacity reached 2,400 rounds across all 6 weapons, with 400 rounds available for the inboard guns and 375 rounds for the outboard weapons. For direct comparison, Germany's Focke-Wulf FW-190 typically carried approximately 2,000 rounds total for its machine guns, plus 500 rounds total for its cannons. The Corsair could fire all 6 guns continuously for approximately 20 seconds before exhausting ammunition, with combined rate of fire approaching 100 rounds per second. The armament installation quality impressed German specialists, who examined the systems according to standard Rechlin evaluation procedures. Spent cartridge cases and disintegrating belt links were collected through chutes and ejected through ports in the wing's lower surface, preventing them from damaging the aircraft or interfering with control surfaces during flight. The mechanism functioned reliably during testing, despite firing thousands of rounds under varying conditions, with no jamming or feeding malfunctions recorded during evaluation programs. Ammunition quality also revealed another dimension of American industrial capability that German engineers had observed repeatedly when examining captured American equipment. The 50 caliber rounds incorporated armor-piercing cores manufactured to consistent specifications, incendiary compounds that functioned reliably across temperature extremes, and tracer elements that burned predictably throughout their flight path. German testing confirmed that American ammunition demonstrated consistently superior reliability compared to equivalent German production, which suffered progressive quality degradation as strategic materials became scarce and production pressures increased. But the inverted gull wings and heavy armament installation represented only external manifestations of the engineering philosophy that German engineers would discover pervaded the entire aircraft. The true revelation awaited when they examined in detail the massive engine that dominated the Corsair's forward fuselage, the Pratt and Whitney R2800 double Wasp that represented American power plant technology at its most sophisticated and capable. This engine would fundamentally challenge German assumptions about achievable power outputs, manufacturing precision, and material quality in production aircraft engines. The R2800 designation referred to the engine's swept volume in cubic inches, 2,800 4.5, equivalent to 45.96 litres of total displacement. For direct comparison, Germany's BMW 801D, the finest radial engine in German production, and the power plant that equipped the formidable Focke-Wulf FW190, displaced 2,560 cubic inches, or 41.8 litres. The American engine was genuinely larger in absolute terms, but displacement alone did not explain the substantial power difference between the engines. The R28008 installed in Mattholie's F4U-1A produced 2,000 horsepower at standard military power settings. With water injection engaged for war emergency power, output increased to 2,250 horsepower. Germany's BMW 801D2 produced approximately 1,730 horsepower at maximum continuous power settings. Even the latest BMW 801 variants with MW50 water methanol injection struggled to approach 2,000 horsepower, and those advanced variants remained rare in operational service through mid-1944. The power differential became even more pronounced when examining later R2800 variants that would eventually equip improved Corsair models. The R280018W installed in the F4U-4 Corsair produced 2,450 horsepower standard, with water methanol injection boosting output beyond 2,800 horsepower. The R280032W, installed in the F4U-5, could generate 2,850 horsepower with full water methanol injection. The title 2,800 horsepower referred not merely to displacement, but to actual power output achievable from the engine family that powered the Corsair throughout its development. German engineers examining the R28008 inches JT404 would discover an engine that incorporated sophistication and quality throughout every component and system. The 18 cylinders, arranged in 2 rows of 9 each around the central crankshaft, featured forged aluminum alloy pistons manufactured to tight tolerances. Sodium-cooled exhaust valves handled extreme temperatures generated during high-power operation. The massive crankshaft, forged from high-grade steel alloy, demonstrated materials and manufacturing quality that German metallurgists examined with professional admiration, while recognizing materials they could no longer obtain in sufficient quantities. Every engine component showed evidence of precision manufacturing to specifications that maintained design intent. Surface finishes were consistently smooth across all parts, indicating machine tools in excellent condition operated by skilled personnel. The magnetos incorporated materials that were increasingly scarce in Germany by 1944. The spark plugs used high-grade ceramics, superior in quality to German equivalents. The direct fuel injection system operated with precision that German engineers associated with laboratory equipment rather than combat aircraft, expected to function reliably under harsh field conditions, including extreme temperatures, vibration, and potential battle damage. Most tellingly, from German perspective, the entire engine showed absolutely no signs of material substitution or quality compromises forced by resource limitations. The Americans had built this engine exactly as originally designed by Pratt and Whitney engineers, using all specified materials and manufacturing processes without any of the desperate improvisations that increasingly characterized late-war German production. Strategic bombing had degraded German industrial capacity steadily, forcing the use of substitute materials, reducing quality control effectiveness, and replacing skilled workers with inadequately trained forced labor. The contrast between German reality and American abundance could not have been more stark. The supercharger system on the R28008 used a two-speed single-stage design that represented American approach to altitude performance in naval fighters. Unlike the turbo supercharger system installed on the Republic P-47 Thunderbolt, which German engineers had examined when captured examples arrived at Rechlin, the Corsair's engine-driven supercharger was more conventional in concept, but the execution demonstrated characteristic American attention to quality and reliability. The supercharger impeller spun at tremendous speeds, compressing intake air to maintain power output as altitude increased and atmospheric pressure decreased. At sea level, the R2800 produced its full rated power of 2,000 horsepower. As altitude increased and air density decreased, engine power output would normally drop substantially. The supercharger compensated for this power loss by forcing additional air into the cylinders, maintaining close to sea-level power output even at moderate altitudes. The two-speed design allowed the supercharger to operate in low gear for takeoff and initial climb, then shift to high gear at higher altitudes where the thin air required more aggressive supercharging to maintain power. The automatic controls managed supercharger operation without requiring constant pilot attention beyond setting desired manifold pressure. German pilots accustomed to manually managing propeller pitch, throttle position, mixture settings, and supercharger engagement on their own aircraft would find the Corsair's level of automation both impressive and somewhat disconcerting. American designers had clearly prioritized reducing pilot workload to allow concentration on tactical situations rather than engine management, accepting the additional complexity and weight of automatic control systems as worthwhile. Investments in operational effectiveness. The propeller installation demonstrated similar attention to sophistication and reliability. The Hamilton Standard Hydromatic constant-speed propeller automatically adjusted blade pitch to maintain optimal engine RPM across varying flight conditions. The system incorporated hydraulic controls, electrical components, and mechanical linkages that worked together seamlessly to optimize propeller efficiency without pilot intervention. The three-bladed propeller with massive 13-foot 4-inch diameter represented one of the largest propellers ever fitted to a single-engine fighter, and it converted the R2800's substantial horsepower into thrust with remarkable efficiency. German test pilots, who would eventually fly the captured Corsair after repairs were completed, would discover an engine that responded smoothly and predictably to throttle inputs, maintained consistent power output across the flight envelope, and demonstrated reliability that exceeded their expectations based on experience with German engines. The R2800's reputation for ruggedness was well earned, American pilots routinely returned to base in Corsairs that had sustained battle damage severe enough to destroy most engines, yet the double Wasp continued producing enough power to keep the aircraft flying. This durability reflected American design philosophy that emphasized redundancy and safety margins throughout the engine. Critical components were stronger than absolutely necessary, providing insurance against unexpected failures or battle damage. Cooling systems incorporated excess capacity to handle extended high-power operation. The radial configuration itself provided inherent redundancy, as damage to one or two cylinders typically did not prevent the remaining cylinders from continuing to function. German engines, designed to extract maximum performance within tight weight and materials budgets, lacked these generous safety margins and suffered accordingly when subjected to the stresses of combat operations. The Corsair's cooling system for the air-cooled radial engine demonstrated characteristic American engineering thoroughness. The massive cowling surrounding the R-2800 incorporated carefully designed baffles that directed cooling airflow across all cylinder heads evenly. Variable position cowl flaps at the rear of the cowling allowed pilots to control cooling airflow, opening them wider for additional cooling during high-power operation, or closing them to reduce drag during cruise flight. An oil cooler with substantial capacity maintained proper lubrication temperatures even during extended combat operations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The entire cooling installation reflected systematic engineering that optimized reliability over minimizing weight or complexity. German engineers noted that American designers appeared willing to add substantial cooling capacity as insurance against operational problems, accepting weight penalties that German designers would have considered excessive. This philosophy extended throughout the aircraft, revealing fundamental differences in design priorities between nations operating under vastly different resource constraints. German technicians working at Rechlin to restore JT-404 to flying condition encountered numerous challenges created by unfamiliarity with American systems and lack of proper documentation. Without access to Vaught's technical manuals, maintenance procedures, or engineering drawings, they relied on careful observation, systematic testing, and professional expertise accumulated through years of working with diverse aircraft types. The process consumed weeks of meticulous effort as specialists examined every system, verified proper operation, and addressed problems discovered during ground testing. The cockpit layout impressed German personnel who examined it during restoration work. American designers had created an ergonomic arrangement with controls positioned within easy reach and instruments grouped logically by function. The seat provided noticeably better comfort than German fighters, an important consideration during multi-hour missions where pilot fatigue could significantly impact performance and decision-making. Visibility from the cockpit, though compromised somewhat by the long nose ahead of the pilot, still exceeded what Messerschmitt Bf 109 pilots experienced with their heavily framed canopies and restricted sightlines. The fuel system demonstrated American attention to operational requirements. The F4U-1A carried internal fuel in fuselage tanks and wing tanks, with total internal capacity providing substantial endurance. External drop tanks could be attached under the centerline to extend range further for ferry flights or long-range missions. The fuel system incorporated multiple pumps, valves, and controls that managed fuel flow automatically, maintaining proper engine feed under varying flight conditions, including negative G maneuvers that could starve engines with simpler fuel systems. By early 1945, German technicians had completed repairs and declared JT-404 ready for initial flight testing. The Corsair received German markings following standard procedures for captured aircraft. American insignia were painted over with Luftwaffe Balkenkreuz on wings and fuselage. Bright yellow identification paint in RLM 0-4 shade was applied to undersurfaces and tail surfaces, standard practice for all captured aircraft, to prevent friendly fire from German anti-aircraft gunners who might otherwise shoot down their own evaluation aircraft. The German test pilot, assigned to conduct initial evaluation flights of the captured Corsair, approached the unfamiliar American fighter with professional caution tempered by curiosity. The cockpit's complexity required study before attempting flight. The instrument panel contained numerous gauges monitoring engine parameters, flight conditions, and system status. Strange levers controlled systems the pilot had never encountered in German designs. The automatic engine management that handled functions German pilots managed manually through constant adjustments seemed almost miraculous, yet potentially confusing. The engine start sequence alone revealed sophistication beyond standard German practice. The R-2800 required specific procedures to properly initialize the massive power plant and its associated systems. The test pilot followed procedures methodically, his engineer's mind cataloguing each step and inferring the purpose of each action based on observed results. When the 18-cylinder radial engine roared to life, it produced a sound utterly different from German inline engines, or even the BMW 801 radial that powered the FW190. This was a deep, powerful rumble that spoke of enormous displacement and tremendous power reserves held in check. The pilot taxied carefully, feeling the weight of the aircraft through the controls. The F4U-1A weighed approximately 9,000 pounds empty, with loaded weight approaching 14,000 pounds with fuel and ammunition. For comparison, the FW190A8 weighed approximately 7,650 pounds empty and roughly 10,800 pounds at maximum loaded weight. The Corsair was genuinely massive for a single-seat fighter, heavier than some twin-engine aircraft in Luftwaffe service. The test pilot advanced throttle for takeoff, and the difference between German and American engineering philosophy became immediately apparent. The R-2800 developed 2,000 horsepower at standard settings with additional power available, through water injection if needed. Despite the Corsair's substantial weight, the massive engine accelerated the fighter down the runway with impressive vigor. The takeoff run was longer than German fighters required, but once the tail lifted and flying speed was achieved, the Corsair transitioned to flight smoothly. Airborne, the German pilot began discovering why American naval aviators and Marine Corps pilots spoke of the Corsair with such confidence, and why Japanese pilots had learned to fear the distinctive bent-wing fighter. The flight controls responded predictably across the speed range. The Corsair accelerated steadily as the pilot climbed away from the airfield, gaining altitude and speed simultaneously. The engine purred smoothly at cruise power settings, demonstrating none of the roughness or vibration that plagued German engines as quality control degraded. At moderate altitudes, the Corsair demonstrated handling characteristics that challenged preconceptions about American aircraft design. The flight controls were beautifully harmonized with aileron, elevator, and rudder forces balanced across the speed range. Control forces increased predictably with speed without becoming excessively heavy, and decreased smoothly at lower speeds without becoming overly sensitive. The aircraft responded crisply to control inputs without displaying oversensitivity or nervous handling. Roll rate particularly impressed the German test pilot. Despite its size and weight, the Corsair could roll faster than most German fighters he had flown. This characteristic, combined with excellent acceleration in dives, created tactical advantages that were immediately apparent even during initial evaluation flights. An American pilot in trouble could roll inverted and dive away at speeds German fighters could not match. The Corsair accelerated rapidly in dives, reaching velocities where German fighters encountered severe compressibility effects that stiffened controls, dangerously. Speed trials conducted under controlled conditions confirmed impressive performance throughout the altitude range. The F4U-1A achieved approximately 417 miles per hour at optimal altitude, significantly faster than the Messerschmitt Bf. 109Gs, approximately 386 miles per hour, or the Focke-Wulf FW190As, approximately 408 miles per hour, when measured under comparable conditions. This substantial speed advantage proved tactically decisive because it allowed Corsair pilots to dictate engagement terms according to their advantage. The climb performance demonstrated capability that concerned German tactical planners who understood the implications. The Corsair maintained excellent climb rates to altitudes exceeding 30,000 feet, where American bomber formations and their escorts operated routinely. German fighters with single-stage superchargers struggled increasingly at these altitudes as their engines lost power in the thin air. The Corsair's engine continued producing substantial power even at extreme altitudes, maintaining full combat capability where German interceptors barely functioned. Dive performance revealed another area where the Corsair demonstrated clear superiority. The aircraft could dive at very high speeds without encountering the severe control stiffening that plagued many fighters approaching maximum design speeds. Pilots could recover from steep high-speed dives without requiring excessive physical effort, and the airframe remained stable throughout without tendency toward flutter or structural failure. This capability eliminated a key German tactical advantage, as diving attacks represented primary doctrine for engaging bomber formations. The structural strength and robust construction impressed German engineers who examined the airframe systematically. The Corsair was substantially built with significant safety margins engineered into critical components. This robust construction philosophy contrasted sharply with German design approaches that often pushed structural limits to absolute minimums, pursuing weight reduction and maximum performance. The F4U could sustain battle damage that would have destroyed lighter German aircraft and still return to base successfully, a capability that translated directly into pilot survival rates and aircraft availability. Turn performance presented a more nuanced picture, requiring careful analysis. The Corsair could not match the sustained turn rate of the Bf 109 inches level flight at moderate speeds, particularly as the German fighter benefited from leading-edge slats that automatically deployed during high angle of attack maneuvering. In sustained, slow-speed turning fights, the lighter Bf 109 held measurable advantage. However, the Corsair's clear superiority in speed and climb rate allowed skilled pilots to avoid sustained turning engagements entirely, fighting instead using energy tactics that maximized American advantages. German test pilots discovered through systematic evaluation that the Corsair excelled at converting speed to altitude and altitude back to speed efficiently, maintaining energy state throughout combat maneuvering. This capability allowed pilots to engage when advantageous and disengage when threatened, forcing combat on their terms rather than accepting the enemy's preferred geometry. The tactical implications were profound and deeply troubling to Luftwaffe commanders who understood that German fighters now had to fight American aircraft that possessed decisive advantages in the parameters that mattered most. Range capabilities astounded German pilots accustomed to severely limited endurance in their own fighters, which rarely exceeded 90 minutes total flight time, including combat. The F4U-1A carried substantially more internal fuel than German fighters, and the aerodynamically efficient design translated fuel capacity into extraordinary range. With external drop tanks, Corsairs could fly missions exceeding 8 hours duration, covering operational distances that seemed nearly impossible to German pilots, whose combat radius barely exceeded 200 miles under optimal conditions. Maintenance accessibility surprised German ground crews familiar with sometimes extraordinarily difficult servicing requirements of German fighters. The Corsair's engine cowling opened to provide excellent access to the R2800 and its accessories. Panels throughout the airframe could be quickly removed to reach internal systems for inspection or repair. The overall design reflected American emphasis on rapid maintenance turnaround and high operational availability, recognizing that aircraft sitting on the ground awaiting repairs contributed nothing to combat effectiveness, regardless of theoretical performance capabilities. The German evaluation of the captured Corsair produced technical reports that circulated within Luftwaffe aviation circles, providing tactical, planners and operational commanders with accurate assessments of American naval fighter capabilities. The reports confirmed what fragmentary combat intelligence had suggested. The Corsair possessed significant performance advantages in critical categories. The aircraft's exceptional speed, powerful engine, heavy armament, robust construction, and extraordinary range created a weapons system optimized for its intended mission of carrier-based fighter operations and ground attack. But the tactical intelligence gathered from testing JT-404 ultimately provided little practical value to Germany's deteriorating war effort by early 1945. Understanding American capabilities did not grant Germany the aluminum, steel, fuel, skilled labor, undamaged factories, and functioning transportation networks needed to produce equivalent aircraft in equivalent quantities. Knowing the Corsair's exact performance did not provide the high-temperature alloys, precision manufacturing equipment, quality control systems, and trained workforce needed to build comparable engines. The captured Corsair represented tangible evidence of American industrial dominance that German pilots and engineers could examine directly. This was not propaganda or exaggerated intelligence reporting. It was an actual aircraft demonstrating engineering achievement and manufacturing quality that exceeded German capabilities across virtually every measurable parameter. The R-2800 engine alone told a complete story about the gap between American and German industrial capacity. Pratt and Whitney, along with license manufacturers Ford Motor Company and others, would produce more than 125,000 R-2800 engines by war's end. Production of this single engine type exceeded Germany's entire combat aircraft engine production for the entire war. BMW produced approximately 61,000 examples of the 801 radial throughout the conflict. American production of one advanced engine type surpassed Germany's total output of all combat aircraft engines combined. American industry in 1944 produced approximately 96,000 aircraft, while Germany reached approximately 25,000 aircraft of all types. The United States built 38,000 fighters alone, plus 16,000 heavy bombers, plus thousands of medium bombers, transports, and trainers. When combined with British and Soviet production, Allied advantage in aircraft manufacturing exceeded 5-1. The industrial base supporting this production operated on a scale Germany could not approach even before strategic bombing degraded manufacturing capacity. The ultimate fate of JT-404 remains unclear in historical records. Some captured aircraft were destroyed during Allied bombing raids against German airfields that intensified dramatically during 1945. Others may have been deliberately destroyed by retreating German forces to prevent recapture. Few possibly survived until war's end and were recovered by advancing Allied forces, though detailed documentation of specific recoveries remains limited. The knowledge gained from systematically examining the captured Corsair provided German engineers with clear understanding of American aviation technology and design philosophy. But this knowledge could not overcome the fundamental disadvantages Germany faced. Intelligence gathering, professional competence, and systematic analysis could not produce the resources, materials, manufacturing capacity, and trained personnel needed to compete with American industrial output and technological capability. The story of the captured Corsair at Rechlin demonstrates how even sophisticated intelligence efforts and professional technical evaluation proved strategically insufficient when facing opponents with overwhelming material advantages. German engineers could examine American equipment, understand American capabilities, and accurately assess American industrial strength. This knowledge was professionally gathered, carefully analyzed, and thoroughly documented. But knowledge alone could not produce the industrial infrastructure required to compete. The F4U Corsair that Lieutenant Mattholie had flown on that July day in 1944 became an instrument of revelation for German aviation specialists. The aircraft demonstrated that American engineers could create highly sophisticated designs that matched or exceeded German capabilities in areas that mattered strategically. The massive R-2800 engine represented power outputs that German engines could not match. The system's integration reflected engineering sophistication that balanced competing requirements successfully. The manufacturing quality demonstrated industrial capacity operating without the resource constraints that crippled German production. The 2,800 horsepower, achievable from advanced R-2800 variants, outclassed everything in German operational service or even advanced development. The BMW 801 peaked at approximately 2,000 horsepower in its most advanced configurations that rarely reached frontline service. American designers had created an engine family that produced substantially more power reliably while demonstrating superior quality and manufacturing consistency. This represented not just engineering achievement, but systematic industrial capability that Germany could observe and document, but never replicate, given strategic circumstances. The Corsair's legacy extended far beyond the specific example captured in Norway. Vought, Goodyear, and Brewster would produce more than 12,500 Corsairs in various models before production ended in 1952, the longest production run of any piston engine fighter in American history. The aircraft served with distinction throughout the Pacific War, achieving an 11-to-1 kill ratio that made it one of the most successful fighters of the conflict. Marine Corps and Navy pilots flying Corsairs destroyed thousands of Japanese aircraft while providing devastating ground support during island campaigns. The F4U continued serving in the Korean War, where it excelled in the ground attack role despite being outclassed by jet fighters in air-to-air combat. French forces flew Corsairs during conflicts in Indochina and Algeria into the 1960s. The aircraft's combination of power, ruggedness, and versatility ensured its operational relevance long after most World War II fighters had been retired. The basic soundness of the design, supported by the reliable R2800 engine, allowed the Corsair to remain effective across multiple conflicts spanning 2 decades. For German engineers examining JT-404 at Rechlin during the war's final months, the Corsair represented a future that had already arrived, one in which American industrial capacity had become the decisive factor in modern warfare. The bent wing, fighter sitting on German soil wearing hasty Balkenkreuz markings over American stars, embodied truths about relative national capabilities that propaganda could not obscure and engineering skill alone could not overcome. The lesson transcended the specific technical details of one aircraft type. The Corsair demonstrated that material abundance, systematically applied through competent engineering and adequate tactical execution, would defeat technical excellence constrained by resource scarcity. The most powerful element in America's arsenal was not any individual weapon, however impressive, but rather the complete industrial system that could conceive, design, develop, produce, and support thousands of complex weapons simultaneously, while maintaining quality and continuously improving designs based on operational experience. When the war ended in May 1945, the captured Corsair's brief second operational life concluded. The aircraft had provided German aviation, specialists with education they desperately needed but received too late to matter strategically. The knowledge arrived when Germany's industrial capacity lay in ruins, its fuel supplies exhausted, its transportation networks destroyed, and its military forces defeated. Understanding American capabilities could not change outcomes already determined by industrial mathematics that no amount of German engineering skill or pilot courage could overcome. Lieutenant Matholie's forced landing in that Norwegian field had placed into German hands one of America's finest fighter aircraft. The examination of JT-404 confirmed what many German aviation professionals already suspected, but official propaganda denied. American engineering had achieved sophistication and quality matching German capabilities, while American industry produced equipment in quantities that rendered isolated examples of technical superiority strategically irrelevant. The 2,800 horsepower R2800 double Wasp that powered the Corsair stood as monument to American industrial might that Germany could document precisely but never hope to match. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this.